Hey everyone, and welcome to the Deep Dive. We're diving into a pretty cool new method for aligning large language models
Yeah.
with human preferences. It's all about this research paper, direct preference optimization, using sparse feature-level constraints.
Sounds a bit intense.
It does sound a little intimidating, but we'll break it down and make it clear.
Yeah, we'll make it fun even. Aligning these increasingly powerful LLMs, it's a crucial challenge in AI.
It's a huge challenge,
Yeah,
making sure they operate in a way that aligns with human values.
exactly. And researchers like Wang et al., actually, they highlighted this in their 2023 work.
Absolutely. And in this paper, the authors, Yin et al., they dive straight into this in their abstract. They point out that aligning these models is at the forefront of AI development.
It really is. We've seen so many different methods emerge, each with its own strengths and weaknesses.
Like take RLHF, for instance, reinforcement learning from human feedback,
Yeah. It's had its successes, but it can be complex.
and computationally expensive.
Yes, as Cristiano Att found way back in 2017.
Then we have DPO, direct preference optimization.
Right. Rofilov et al. Explored that one in depth in 2024. DPO streamlines things a bit.
It bypasses the whole reward model setup of RLHF, making it more efficient.
Exactly. But there's always room for improvement. And that's where this new method, FPO, comes in. Feature-level, constrained, direct preference optimization. It focuses on simplifying that whole alignment process.
But making sure it's still effective.
Right.
Okay, so let's break down what FPO actually is. The abstract lays out its core aim, simplifying alignment while ensuring stability. They achieve this by using pre-trained sparse autoencoders, SAEs for short, and introducing these feature-level constraints.
So imagine these SAEs as filters. Powerful filters that can extract the most important features from all that data that the LLM processes.
Instead of dealing with all that data, FPO cleverly uses these sparse features, activated in a well-trained SAE, to make those really targeted adjustments to the model.
And that leads to a really great balance between efficiency and controllability, something previous methods really struggled with.
The authors actually visualized this comparison in Figure 1 of the paper.
It's really helpful to see it laid out like that.
Now, I know we're using a lot of technical terms, so let's unpack the building blocks of FPO. Section 2 of the paper, Preliminary.
Okay. So they lay the groundwork there, explaining how methods like DPO, SIMPO, and TDPO work. Each of these tackles alignment a bit differently.
Like SIMPO, Equation 3 uses a technique called length normalization to simplify calculations, a really clever way to streamline things.
And FPO borrows this idea, incorporates length normalization from SIMPO to boost its own efficiency.
It's like FPO is a hybrid, taking the best parts from different methods and combining them.
Exactly. And it also borrows the concept of a reference model from DPO, but with a twist. Instead of loading the entire reference model during training, which can be computationally heavy, FPO pre-computes and stores the key reference data.
You can find the details on that in the sections DPO with reference-based target margin and building offline reference margin and constraint. It's like having a cheat sheet with all the essential info from the reference model, making the process so much faster.
Precisely.
Now, let's talk about how FPO uses constraints. Instead of using the computationally expensive KL divergence that's used in TDPO, FPO opts for the MSE, the mean squared error of sparse activations from the SAE. You can see that in Equation 12 in the feature-level constraint section.
Basically, it's a more efficient way to guide the model's behavior without giving up effectiveness.
Exactly. And this whole focus on efficiency is really apparent when we look at the hardware requirements. Figure 4 on the left and the hardware efficiency of FPO section show that FPO uses significantly less memory and computational resources than TDPO,
Which is huge because it means FPO could be used on smaller devices.
opening up all sorts of possibilities for personalized AI applications.
Like imagine FPO running on your phone. That's the kind of potential we're talking about.
Making powerful AI more accessible, more integrated into our everyday lives.
Now we know it's designed to be efficient, but how well does it actually perform? The researchers put it to the test, and the results are pretty impressive.
They evaluated FPO on benchmark datasets like AlpaCable 2, Arena Hard, and MTBench.
Section 5 of the paper goes into all the details.
Okay.
And Table 2 shows that FPO consistently outperformed the existing methods. It actually achieved up to a 5% absolute improvement in something called win rate.
To clarify for our listeners, these benchmarks evaluate the model's ability to follow instructions, generate human-like text, and essentially demonstrate their understanding and responsiveness to those human preferences.
Exactly. And the win rate basically tells you how often the model's output is preferred over the output of other models based on human evaluation. So a 5% improvement is a big deal.
It really showcases the effectiveness of FPO's approach.
Now, one interesting observation they made was that FPO's performance boost was even more pronounced on the 2B model compared to the 9B model. They think this could be because the smaller model might be better at filtering out noisy or irrelevant features, leading to more precise constraints.
So it's not just about the size of the model. It's about how well it can focus on the right information.
Exactly. And speaking of nuances, the researchers also looked at how FPO balances accuracy with diversity in its generated text.
This is discussed in Section 5.1, with results shown in Table 3.
It's a crucial aspect of alignment because we want LLMs that are not only accurate, but can generate creative and diverse outputs.
We don't want AI that just spits out the same robotic responses.
We want AI that can surprise us, think outside the box, while still sticking to human values and preferences.
It sounds like FPO is making progress in that direction. It's not just about getting the right answer. It's about generating engaging text that reflects how rich human language is.
Absolutely.
Now, to understand FPO even better, the researchers did what's called an ablation study, which they detail in Section 5.2.
Basically, an ablation study is systematically removing or changing different parts of a system to understand what each part contributes to the overall performance.
So in this case, they were looking at the placement of the SAE encoder within the model's architecture and the influence of a parameter called alpha.
And their findings are in Table 4. Some interesting insights there.
They found that placing the SAE encoder closer to the final output layer led to better performance. This suggests that capturing features at that stage is crucial for effective alignment.
Right. It's like making sure you're making adjustments at the right point in the process.
Exactly. They also found that the choice of alpha, which controls the strength of the constraints, had a significant impact on the balance between accuracy and diversity.
A higher alpha value, meaning stronger constraints, led to higher accuracy, but might sacrifice some diversity, while a lower alpha value gave the model more freedom to explore, but maybe at the risk of straying from the desired path.
It's like finding that balance between control and freedom.
Right. They determined that an alpha value of 0.5 struck the best balance between these two, showing how important careful parameter tuning is.
It's like fine-tuning an instrument to get just the right sound.
Exactly. And this careful tuning is one of the reasons why FPO is so effective. It's not a one-size-fits-all solution. It's a framework that can be tailored to achieve optimal performance for specific tasks and data sets.
Now, before we get into those temperature comparison experiments in Part 2, I'm curious to hear your thoughts on the significance of this ablation study.
Well, to me, what stands out is that even small changes to the FPO architecture can significantly impact its performance. It shows how important careful design and fine-tuning are when you implement this method.
Like fine-tuning a race car to get that extra edge. Each element plays a role in achieving optimal results.
Exactly. Welcome back to the deep dive. We're going even deeper into those technical details of FPO, so let's pick up where we left off and explore those temperature comparison experiments.
Sounds good. Could you remind our listeners what temperature means in this context? We briefly touched on it in Part 1.
Sure. So in the world of LLMs, temperature is a parameter. It controls the randomness of the model's output.
Okay.
A higher temperature means more randomness.
Leading to more creative and diverse text.
Yeah, potentially, but maybe at the expense of accuracy. And conversely, a lower temperature, it leads to more deterministic and predictable output, but maybe less exciting or creative.
Okay, so it's this trade-off between predictability and creative freedom for the model.
Exactly. So the researchers wanted to see how FPO would perform under different temperature settings. They did a series of experiments. They used the Arena Hard dataset, and they tested 5 different temperatures, ranging from 0.2 to 1.0.
And they brought in GPT-4 Turbo to be the judge, evaluating the outputs of FPO compared to other methods.
Right. And the results, figure 4 on the right, were pretty impressive. FPO consistently outperformed those other methods across those different temperature settings.
So FPO can handle the heat, so to speak, no matter how high the temperature gets.
It can. This ability to perform well under different temperatures, it's really crucial for real-world applications. You know, we want AI systems that are flexible.
Adaptable to different contexts and user preferences.
Exactly.
Before we move on, let's step back for a second and think about how FPO fits into the broader research landscape.
That's a great point. Section 6, Related Work, gives a helpful overview of how preference optimization methods have evolved.
Okay.
They start with RLHF, highlighting its early contributions. Researchers like Ouyang et al. Explored this.
And then they trace the progression to DPO and its different forms like KTO and token-level DPO, each one addressing those specific challenges in alignment.
Right.
And then we see more efficient methods emerge like ORPO and SIMPO, aiming to streamline that alignment process.
But what sets FPO apart is that clever combination of efficiency and controllability.
It's like FPO represents this big step forward, building on the strengths of previous methods while introducing its own unique approach.
Exactly. And in addition to preference optimization, FPO is connected to LLM interpretability, which is also discussed in Section 6.
Interpretability, the quest to understand how these AI systems work.
Right. Peering into the black box to figure out their decision-making.
Researchers are using techniques like sparse autoencoders, the SAEs that are so central to FPO, to gain insights into the inner workings of LLMs.
It's like using a microscope to examine these intricate mechanisms of AI.
And research by Marks et al. Has shown that aligned LLMs actually learn specific feedback features related to human preferences. It helps explain that improved alignment.
So it's not just blindly optimizing the model, it's understanding how the model is learning and adapting to align with those human values.
Absolutely. Let's shift gears now and talk about the theoretical underpinnings of FPO.
Okay.
Getting a little more technical here.
The authors, Yin et al., they were very thorough. They provided those experimental results, but also a solid theoretical foundation for FPO. They actually included a whole section in the appendix, bounding tail divergence with MSE of sparse activation.
Sounds intense.
It dives into all those mathematical details.
Okay, let's unpack this.
For those who don't know, KL divergence basically measures how different two probability distributions are from each other.
Okay.
It's a key concept in information theory. And it's often used in machine learning, especially when aligning models or optimizing policies.
So it helps us understand how far off the model's output is from the ideal output.
Precisely. Now, the big question they tackled in the appendix, can we use the MSE of sparse activations from the SAE to limit the KL divergence between the model's output and the reference model's output?
So basically, can we use a simpler calculation, MSE, as a stand-in for that more complex KL divergence calculation?
Exactly. And that's where Theorem 1 comes in. It's the backbone of this idea. The theorem states that under certain conditions, minimizing the RSE between those sparse activation values actually leads to a reduction in the upper bound of the KL divergence between the token probability distributions of the two models.
Okay, some listeners might be feeling overwhelmed by the technical terms. Let's break this down a bit.
Okay.
First, we need to understand sparse activations. These are the outputs of the SAE after it processes the model's hidden representations. This definition is laid out in equation 14.
So the SAE extracts the most important information from the model's internal workings.
The essence.
Exactly. They also define token logits and probabilities in equation 15. Token logits are the raw output of the model. Then they are converted into probabilities. That represents the model's confidence in generating each possible word in its vocabulary.
It's like the model is saying, I'm this much sure that the next word should be this.
Exactly. And they provide a formal definition of KL divergence in equation 16 for those who want to go deeper.
But here's where things get interesting. Before they go into the proof of Theorem 1, they set out 3 conditions that have to be met for this whole thing to work.
Like setting the stage.
The first condition is all about making sure that SAE is doing its job. Accurately reconstructing the model's hidden representations. They call this accurate reconstruction. And they quantify it using a small value epsilon, which represents the maximum allowable error in the reconstruction.
Like saying, hey, SAE, you better be capturing the essence of these hidden representations.
Or the whole theorem falls apart.
Exactly. The second condition is bounded operator norm. It's defined in equation 18. It basically ensures that the math doesn't blow up to infinity.
A safety net.
Right. And the third condition, small logit differences, says that the difference between those logits produced by the model being aligned and the reference model should be pretty small. This makes sense because they were using a tiny learning rate during that alignment training, so the changes to the model are very gradual.
Small control steps.
Yeah.
Okay, conditions are laid out. They start the main proof of the theorem. I'm not going to go through every single step, but I'll highlight the key insights.
Okay. The proof relies on a few lemmas. Basically, mini-proofs that build up to the main conclusion.
The first one, lemma 1, shows that under that accurate reconstruction condition, The difference between the hidden representations of the two models can be approximated using the difference between their sparse activations. You can see that in equation 19.
If this SAE is working well, we can use those sparse activations as a substitute for the actual hidden representations.
Then lemma 2 connects the difference in logits and the difference in sparse activations using a matrix denoted by K. This is in equation 20.
This connection is important. It links those sparse activations, which we're using as a proxy for the hidden representations, to the logits, which determine the model's output probabilities.
And lastly, lemma 3 gives us a way to bound the KL divergence using the difference in logits, assuming that difference is small, as stated in condition 3. Equation 21 shows that relationship.
Putting it all together, they combine these lemmas to show that by minimizing the MSE of those sparse activations, you ultimately minimize an upper bound on the KL divergence between the output probability distributions of the two models. It demonstrates the theory behind FPO's approach.
It's fascinating how they've connected sparse activations to KL divergence mathematically.
Yeah, and this connection is crucial to FPO's efficiency. By using the MSE of sparse activations as a constraint, they avoid that really computationally expensive task of calculating the KL divergence directly, which would mean dealing with huge probability distributions over the whole vocabulary.
So it's about making the whole alignment process more feasible computationally.
Exactly. And this efficiency makes FPO potentially viable for smaller devices, which opens up new possibilities for personalized AI.
Okay. Let's move on from the theoretical and discuss the experimental setup, detailed in section 4.
All right. To test FPO, they were very careful in their model selection and training. They chose models with different parameter sizes, 2B and 9B versions of Gemma 2, to test how scalable their method was. They started with those foundational models that were brand new. No prior fine-tuning or alignment.
A clean slate.
Exactly. They first fine-tuned these models. They used a conversational format from the Halos dataset, and they applied it to UltraChat 200K, which established a baseline conversational ability.
So that gave them a solid base to work with.
Right. Then they used the ultrafeedback dataset to align these models using different methods, including FPO.
To evaluate the performance of those aligned models, they chose 3 well-known benchmarks: MT Bench, AlphaKeval 2, and Arena Hard.
These benchmarks push the models to their limits, testing how well they follow instructions, how human-like their text is, and how they handle different tasks.
They used human evaluation, with GPT-4 Turbo as the judge, to check the quality and coherence of the model's output.
So a robust evaluation process.
And the results, detailed in section 5, were quite impressive.
FPO consistently outperformed the other methods, achieving big improvements in accuracy and diversity across all 3 benchmarks.
And in some cases, those improvements were huge, up to a 5% increase in win rate.
Right. That win rate tells us how often the model's output is preferred based on human evaluation. So a 5% increase is really significant.
Shows how effective FPO is.
They also measured the balance between accuracy and diversity.
We talked about that. The need for models that are accurate and capable of generating diverse and interesting output.
Yeah. They quantified this balance by measuring the accuracy on the ultrafeedback dataset and also the entropy of the generated text on AlphaKeval 2.
Okay.
Higher entropy basically means more diversity in the model's output. It's a good way to measure its creative freedom.
And Table 3 has the results. What did they find?
Well, FPO got the second highest training accuracy, just behind TDPO2, but it had the highest diversity among all the methods they tested.
Finding that sweet spot between being accurate and creative.
Yeah, and that's a really promising finding.
Now, before we finish part 2, let's talk about FPO's hardware efficiency.
Right. Remember how we said FPO was designed to be computationally friendly? Well, they put this to the test by measuring how much memory different methods use during training.
Figure 4 on the left shows those results, and they're pretty encouraging. FPO used a lot less memory than methods like TDPO.
Yeah, around a 17% memory optimization. This efficiency comes from 2 main design choices: offline processing and sparsity.
Could you explain those a bit more?
Sure. Offline processing means they calculated and stored all the necessary info from the reference model ahead of time, so they didn't need to load the whole thing during training.
Like having that cheat sheet.
Right. And sparsity means that the SAE only uses a small set of its features for each input.
So it focuses on what's important.
Exactly. And together, offline processing and sparsity make FPO a more practical approach to aligning LLMs.
Potentially allowing us to run these powerful models on smaller, cheaper devices, making AI more available.
Exactly. That brings us to the end of part 2. We looked at the theoretical foundations of FPO, the experimental setup and results, and we examined its hardware efficiency.
We've covered a lot, but there's still more to discuss. Join us in part 3, where we'll wrap things up by going deeper into that ablation study. Welcome back to the deep dive. In this final part, we'll take a closer look at the ablation study, what it tells us about how FPO works.
Yeah, it's a really important part of the research. It helps isolate the impact of different parts of FPO.
Right, like taking something apart to see how each piece contributes.
Exactly. As we mentioned in part 2, Yin et al. Focused on two key aspects of FPO, the placement of that SAE encoder and the impact of alpha, that parameter that controls the strength of the constraints.
And Table 4 shows their findings, some really valuable insights.
One of the biggest was that where you put the SAE encoder really matters. Putting it closer to the output layer led to much better results.
So the position of the SAE encoder is crucial.
It is. The researchers think this is because those later layers are more important in shaping the final output. So capturing features there makes the alignment more precise.
Like making sure you're adjusting the right part of the system?
A good analogy. They also found that choosing alpha, which controls how strong the constraints are, really affected the balance between accuracy and diversity.
Right, that balance we talked about before. We want models that are accurate, but can also generate varied and interesting output.
Exactly. The study showed that a higher alpha, stronger constraints, meant higher accuracy, but potentially less diversity.
Trade-off, then.
Yeah. A lower alpha gave the model more freedom, but maybe at the risk of those outputs being less accurate.
Finding that balance between control and freedom.
Exactly. An alpha of this 0.5 seemed to be the sweet spot, the best balance between accuracy and diversity. It shows how important it is to fine-tune those parameters.
Like fine-tuning an instrument.
Exactly. This careful tuning makes FPO so effective. It's not just one size fits all. It can be tailored to different tasks and data sets.
Okay, so beyond the ablation study, they also tested how robust FPO is under different conditions, which is where those temperature experiments come in.
Right, remember, temperature controls how random the output is. Higher temperature, more randomness.
They tested FPO across different temperatures, from 0.2 to 1 point ever, using the Arena Hard dataset. GPT-4 Turbo evaluated the outputs.
And the results, in Figure 4 on the right, show that FPO consistently outperformed other methods across all the different temperatures.
So FPO is adaptable. It can handle different levels of randomness.
Exactly. That's crucial for real-world applications where conditions aren't always perfect.
Well, I think we've covered a lot in our deep dive into FPO. We've talked about efficiency, effectiveness, the theoretical foundations, and its robustness.
It's been a fascinating look at how this field is changing. FPO looks like a promising step forward.
I agree. It's exciting to see these new techniques being developed to make sure these powerful language models align with human values and preferences.
And as these models become more advanced and integrated into our lives, alignment will only become more critical.
Absolutely. We need to make sure these technologies are developed and used responsibly, and research like this is paving the way for AI to benefit humanity.
Well said.
Thank you, everyone, for joining us on this deep dive. We hope you found it informative.
And as always, keep exploring and learning about this amazing world of AI.
Until next time.